Okay, folks, we're going to get started again. Welcome to Wednesday afternoon, middle of the week, right after lunch. The best time to do interactive activities to keep you awake. We're going to do hands-on session number 2 today, focused on putting your interesting event into galactic context. How do you turn all of those microlensing or transit fit parameters you were working on yesterday into astrophysical properties that might tell you something about planet mass functions or period distributions, etc. Okay, so to get started, make sure you follow all the same instructions as yesterday. In the Slack Hands-On Session 2 channel, you can find a link to the instructions for this activity. Those are PDF notes for where to go. It has all the links in it, but if you can't find it, it's also in the Slack right there. Click link to open folder in your browser. So go ahead and do that. And then you'll need to make a copy of the primary notebook, which is called Session 2 Project. So make a copy to that and put it into your own Google Drive. So the instructions are here. You can either add a shortcut to your drive. You can download it as a Jupyter Notebook if you'd rather run it that way. But it should work on Google Colab. There's a lot of data files that the workbooks will need, so it's best to do it on Google Colab if you haven't already downloaded everything. Okay, I'll just give you 2 minutes to do that.
Melanie renamed it to this one, Hands-On to...
Hands-On 2 group project?
No, sorry, this one, Hands-On to ML or transit context. Sorry.
Okay, yeah. It's correct in the PDF, so look there.
Yeah.
And when you've got a copy of the notebook copied over, just give me a thumbs up so I can keep tabs. You don't have to keep it up. I got you. One of how many? Thanks. Any more thumbs up? There were a few people. Yeah, good. Thanks. Thanks. Up front over here or very back row? Good? Yeah? Very back row, you guys got the notebook copied over? Yeah? Excellent. Okay, I think we've got a majority now. Anyone stuck and have a major issue getting the notebook copied? Okay, great. Okay, so microlens or transit event in context. So once we detect a microlensing event, we've run all our fits on it. For instance, we're going to say microlensing event a lot here. You can just substitute or transit or any other interesting phenomena in Roman you might be interested in of a stellar nature into when we say that. So once you've detected an event, we want to know everything we can about the object. If it's either a transit or a microlensing event, we have multiple objects that are typically within the spatial resolution element of Roman. It might be the background source star and the foreground lens. In a transit, it's both the transiting foreground thing and the host primary star. We want to know how far away is it. We want to know what kind of star is it, what's its mass, what's its age, ideally what's its metallicity, how is it moving through the galaxy. All of these allow us to put it into an astrophysical theory and test that theory. So we definitely want to take this step on all of our events. Unfortunately, most of these things don't come out of the catalogs by default. You don't get a catalog that says, for your event, here are all these properties. You have to derive those yourself, and that's really what you're going to do today in the group activity. So we're going to use the things that do come out of the catalogs to constrain the physical properties. The things that come out of the catalogs are photometry, how bright something is, what's its color. Astrometry, what's its proper motion, and in some cases, parallax. And that might be it. And we have to turn all of those into these really a large suite of physical properties. Okay, so the first thing is we just need to load up some packages. So go ahead and run the first imports. You'll notice we're using NumPy, Matplotlib for plotting, and AstroPy for various table munging and coordinates manipulations. You'll also be accessing a lot of mock Roman data along with some simulation data. So you'll need to make connections to that. That's cell number 2. Go ahead and run that, and you're going to have to get authorized on your Google account. But at the end, it should say mounted at /content/drive if it was successful. It should create a pop-up window, so look out for that pop-up window if you've got it blocked. Anyone having trouble with the authorization or good to go? Thumbs up is welcome. Good, good, good. Great. Anyone stuck? Okay. Now, machinery aside, now we're getting into the real meat of it. We're going to introduce you first to the data set. So we've generated some mock Roman data. Obviously, Roman hasn't launched yet. We don't have the real stuff. I will say a couple of caveats about the mock data. We have, for the most part, not included uncertainties in the quantities that you're going to be working with today. We'll call that an advanced feature, but most of the Roman data, all the parameters will come with uncertainties along with them. Also, the names of the columns in the table you're going to load are not necessarily matched yet to the names of the columns that will be in the true mock data, the true Roman data, and that's largely because they were in definition at the time we were writing these notebooks. They're still deciding on what those column names are. So just watch out for that. You can't run this notebook on day 1 of Roman data release. You'll have to swap some things around. Okay, so what is Roman likely to give us? The table of detected microlensing events, or hopefully transits, but we know the microlensing events will come out. And it'll come out with a set of best fit parameters. A lot of these parameters you should be familiar with from your work yesterday. You'll have the projected closest approach, U0, in units of theta e, or the Einstein radius. You'll have the time of closest approach, T0, the Einstein crossing time, the microlensing parallax, the Einstein radius. Anyone remember, do we get Einstein radii for all microlensing events? Feel free to shout out an answer. Which ones do we get Einstein radii for? Binary stars, yeah, that's right. Things with planets or with companions of any kind. In the photometry, that's it. And in fact, it's not even all binary stars. It's only binary stars that have multi-peaks, clear or near caustic crossings. Okay, so we've already culled this down to a set of events where you have theta E4. Presumably, at least for planets, those are the ones you're interested in learning the most about. And then all of the photometry, that's going to come in the form of the baseline magnitude. Baseline magnitude means it's the magnitude you actually observed within a resolution element for Roman. And it comes in a bunch of different filters. That's what the underscore star is for, and all of that's in AB magnitudes. And then we've done some of the legwork of splitting out the lens and source flux for you based on the blend fraction, the source flux fraction that I think you talked about only a little bit yesterday, but that was in a lot of your lecture notes. Okay, so that has no uncertainties in this table, but in reality, that's going to be a large source of uncertainty for a lot of events. The two proper motions, again, are already decomposed for the lens and source, again, using that blending parameter. Again, for real events, that will be a little more uncertain than might be conveyed through this table. Okay, that's everything in the table. Go ahead and try to load the table. Make sure you can read it from Google Drive, and then display it, and you should see something along the lines of this big old table with all those columns we just discussed. As you're looking at that table and making sure it loads up, anyone have any questions about any of the values you see already? Spot some odd and weird things about the data? Anyone see an unusual entry in the data table? You can raise your hand once you do.
I think we might want to let people know to make a shortcut from their personal drive to the data locations. Some people are getting errors because they can't access our folder directly.
Okay, yeah, so some folks online are having the trouble where the data folder is not in their own Google Drive. So just like you made a shortcut to the individual notebook, what you really should do is make a shortcut probably to the whole folder, which is I think what the instructions say. So make sure you've made a shortcut to the whole folder, or if you want to get if you've already committed, then do it for each of the subfolders with the data in it. But really the whole folder is best. Yep. Okay, did you spot something unusual in the data table, or did you have a trouble loading the data? Okay, good. Is it the NANs? Yeah, there are some NANs. Anyone have thoughts about why there should be NANs? In this case, it's a NAN on the blend parameter. Why should we not be able to get a blend parameter out? Might just be a bad fit to the data. Could be that it's such a small or such a large blend fraction we can't get a reasonable quantity out. I actually don't know. Is this one a dark lens? Is that why?
This one, the magnitude is too dim in that specific filter.
Yeah.
To get a light curve.
Yeah. So for those online, that particular one, you'll notice there's a blend fraction for each filter, but you have to have a light curve in the filter. And so for this one, it was too faint in the F087 filter. We had a question in the back middle, or an unusual item? Uh-huh. Yeah, Macy, you want to run up and see? Good. Yeah. Okay, who else has the table up and displayed? Give me a thumbs up if you got the table displaying. And we have a couple more with issues on the data table, is that right, at the top? Yeah. Okay, for folks who are still having data drive issues, once you put the whole drive, the whole folder for the whole activity, add it as a link into your own Google Drive, you'll need to change the path. There's a variable up here called data directory. Make sure that's pointing to your directory location, not mine. Mine says content, drive, shared drives, da 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 da. You need to change that variable to point to your directory.
Even though the version that Melanie made, she did already do content drive, my drive. So she already did that. So it should be already working. Like it worked for me.
Yeah, I don't know why.
They don't work
Some of
for
them
them?
are having to add the whole
It's different,
thing.
really?
I think one of the links Melanie sent around pointed to our version of the notebook, not her version of the notebook.
Okay.
So that might be a problem.
But that's from a PDF file because I just.
Yes, that's right. So from the PDF, I think it's okay, but in Slack, it's not.
Oh,
So
okay.
if you can message her.
Yes.
Okay, so if you're having data drive issues still, can you raise your hand so we'll send someone your way? Right here is one, and back there is another. Any others? And also in the middle, we have two still. Yeah, that would be great. Okay, so we're going to keep going. Okay, so everyone on the tables, you have to pick an event you want to work with. So we've got a recommended event number there that will behave well for the rest of this activity. If you're adventurous, you can pick a different number, but I would recommend sticking with the number we specified until you get to the group projects. While we're waiting here for just another 2 minutes, you can explore this event if you like. Yeah, so make sure you opened the notebook from, we're just discovering this now, from the PDF. The link that is in the Slack message appears to be the wrong link. It's to a different version. It should still work, but it's got a different path on it. That's why it's not working for you. So copy the notebook from the PDF. Two in the middle here. So in the meantime, you can look at your event. Oops, did it not load for me? Oh, events table. Okay. Who is still in process of getting the data to load? Raise your hand if you're still in process of getting the data to load. Okay, great. We're going to keep going. Okay, so now you've loaded your list of events. There's other data that comes with Roman, and this data is just as important. It's not just the events of interest. It's everything for every star that flows around your event of interest. And this is how we're going to place things into context. They give us a lot of clues about the event properties. So this is a catalog of stars, the stars table. Caveat, not all stars are actually stars. These are actually star systems. Most of the time, they're going to be multiple stars per spatial resolution element. So just keep that in mind, but we're going to call it the stars table. So these are all the detected stars in the subfield we're focused on. So basically everything within I think it was a 1 arc minute or 30 arc second patch of the events. We've shrunk it down so it's manageable for the class. These tables will be huge for the real Roman data. The stars tables don't just include the microlensing or transit events. It does include your events too, but it also includes everything that wasn't an event. And as I said, they're blended combinations of multiple stars, and the proper motions and parallaxes for those stars can be the flux-weighted sum of multiple stars' proper motions and parallaxes. The columns in here are a little more confined. We're basically getting a name of a star, hopefully that we can tie across all the images that Roman ever takes. The star will always have the same star name. The coordinates on the sky, galactic latitude and longitude in this case. Proper motions, note we're working in galactic coordinates here. The real Roman data, we're not sure, but I think it comes in RA and DEC, not galactic latitude and longitude. but easy enough to convert. Proper motions, parallax, and the photometry in all the filters. So make sure you can load the stars table. You'll notice the stars table comes in, and the events table come in Parquet format. You might ask, why isn't it just a giant text file that I can read with my human eyes? And that's because text is really fat when it comes to storage on a disk, and so we prefer binary formats, and Parquet is a nice one to work with. You can use pandas, you can use AstroPy tables, just about anything these days will load Parquet. And when you display the stars table, you should see things like this. Again, once you get it loaded, give me a thumbs up or a hands up and tell me something weird you see in the table. Yeah, why 99s? What can the 99s possibly indicate? Too faint to detect for Roman. So the reason they're still in the table is because they're detected in at least one filter of Roman. What's something you notice about all the filters? So if we see, here's the shortest wavelength filter, which is 620 nanometers, 870, 1 micron, 1.3 microns, 1.6, 1.46, that's the wide one, and then all the way to 2 microns. What do you notice about the properties of the 99s? Yeah, go ahead. More 99s in the blue filters, in the short wavelength filters. Why? Channel David Nataf, yes. Extinction. Reddening makes it so that it's harder to see stars towards the bulge in the blue filters, a lot more 99s as a result. Okay, now pick out your event. Your event has the same name, it's the same star ID in the events table and the star table. So that's how we can connect the two. So we've done that up above. We found where our event is. In this case, yeah, there we go. It should match 1292370. Should match up here our little index 1292370. Okay, now we've got our events, we've got the surrounding stars. The next order of business is to make a color magnitude diagram. We want to see what the stars look like surrounding our event. So that's your first task, is to make a color magnitude diagram using the stars table to show where your event is going to land. So ideally, your color magnitude diagram would have color on the horizontal axis, magnitude on the vertical axis. You've seen lots of these in the talks. And if you can get to it, put your event on there as well with a different color. We'll give you about 5 minutes to do this, or Gemini can do it for you in 30 seconds. Okay, so as I said, color magnitude diagram, color magnitude. Give it a chance to make the figure if you can. Typically, when we do color plots, we plot the blue minus the red filter. It's your decision which set of filters you like to plot. But remember what I said about extinction. It's harder to find a lot of stars in the blue filters. The red filters, many more stars are detected. So if you have to choose, I would choose the reddest and the not quite the reddest, but maybe middle of the road filter. And then we'll go through what that tells us in just a moment. And I'll give you another 2 minutes and then show some code. If you've got one plotted and you're ambitious, you can actually look at color magnitude diagrams in multiple filter sets and put your object on all of them. Okay, so for a color magnitude diagram, pretty simple plotting commands, but really what I've plotted here is the color in the 158 filter and the 213 filter. So that's 1.58 microns and 2.13 microns as the color on the horizontal axis, and then the vertical axis is 213. That's the typical convention where we do a blue filter minus the red filter, and then the red filter on the horizontal axis. But sometimes you'll see it swapped. All right, this is the color magnitude diagram I get before I put the event on. Let's talk a little bit about what we see. Are people familiar with the main sequence of stellar evolution? Give me a hand raise if you are familiar with the main sequence. Okay, we'll call it 90%. But for those of you who aren't, the main sequence is where stars sit when they're spending most of their life from birth, or nearly very shortly after birth, through all of their adulthood and before they start to evolve and change their internal structure. Main sequence is where the star is burning hydrogen at its core, fundamentally. And what's really nice is in color magnitude diagram space, stars sit on this main sequence. They make a line where at the top, usually the most massive stars sit, and at the bottom, the lowest mass stars sit. So this is a color magnitude diagram in the infrared, and we see a sequence that looks sort of like that, but it's really fat and wide. Why would it not be a nice line like a normal color magnitude diagram you might have seen from Gaia, for instance? Any thoughts? Why is it so fat? Not all at the same distance, right? We're looking at an integrated stellar population through a giant soda straw, right? And everything's at different distances. What else? Why else would they spread around on here? Back to David's talk. What was it? Differences in reddening, right? So when a star has a different amount of gas in front of it than the neighbor star, as a result, the star will look both fainter and redder. Stars move down and to the right as you put more gas between us and them. So that's why we get this really, really fat sequence kind of all along the way. What about this big turnoff here? Any ideas? Anyone familiar with why we see two branches? What's that second branch? What was that? I heard someone say it. Giant branch, yeah. So what happens when stars stop burning hydrogen? Their cores collapse a little, and then their outskirts inflate, and they turn into giant stars. That's later in their life. That's what we call old age for stars, right before they die. And the red giant branch is what this second sequence is. Okay, now bonus points. Does anyone know what the weird clump is? It's called the red clump. Yeah, I gave you the clue. It's called the red clump. Now, does anyone know what the red clump is? Hopefully you know it's used for extinction measurements, because David told you that yesterday. Anyone know what the red clump is? Core helium burning, yeah, great. So when a star is no longer burning hydrogen, there's a short period where it's doing hydrogen burning in a shell, but it's kind of inert still in the middle. That's the normal red giant branch, and stars move up and down of the same mass. They move up and down this branch over time. But there's a period in which the hydrogen burning kind of peters out a little, the core starts to collapse, and helium ignites, and that helium ignition tends to occur right here. Now, for stars of low metallicity, the helium ignition actually can occur in a lot of different places along this branch, but as you go to higher metallicities, it becomes quite predictable when helium ignition occurs, and that's why all the stars like to clump in one physical spot, the same absolute luminosity. Now, in this particular color, it's pretty horizontal, but if you change your filter set, some of you may have plotted different filters, you might see it more of a diagonal line. And again, those stars all have the same absolute luminosity, but a little bit of different reddening, a little bit of different gases in front of us, in front of each star will stretch that along the reddening vector. So that's what David was talking about when he was saying you can use this spread to measure the reddening for individual stars or patches in the sky. Okay, color magnitude diagrams are fascinating. We've learned a lot about stellar evolution from them. Main sequence, red giant branch, red clump. Spreads come from different distances and different extinctions. Where's your object on this? Oops. Oh, yes, it was. Sorry, mine expired, so now it's not going to work. So hopefully you've put your object on it. If you have not, go ahead and do that now. Now, when you decide to put your object on here, what column should you be using from the events table? If I go back up to the events, how do you put your event on here? So obviously you're going to use magnitude columns, but which one do you use? Base, lens, or source? You can start with base. That's what we're observing. That's definitely worth putting on there just to see to begin with. But if we want to make physical sense out of it, what do we put on? We have to use lens and source separately because we want to know something about the lens or the source. What do we care more about in this case? The lens. It's the lens host star. If this thing hosts a planet, we want to know where it sits. We want to know its age and its distance. So go ahead and plot all three. Hopefully you've got that on. And it should, if you use the same event as we did, look something like this, where the blended baseline flux is up here. Then when you separate it into lens and source, you'll see that for this particular event, most of the light is actually coming from the lens, not from the source. Okay, raise your hand or give me a thumbs up if you've got your lens or source or blend plotted on a color magnitude diagram. Still working on it. Okay, we'll give you a few minutes. Anyone still working on getting their object on the CMD? Okay. Yeah, so for those who are online, make sure remember this CMD is a mix of the stars table, that's everything in black, and the blue, red, and green points on here are coming from the events table. So we're putting magnitudes in from both tables, because only the events table tells us the separated source and lens brightness. What was that? Yeah, no problem. There you go. Get it out of the way. So the most important is for the individual lens and source fluxes. Those have to come from the events table. All right, now who has either their event, their lens, or their source plotted on the color magnitude diagram? Okay, we'll give it another 2 minutes. For those who are done, you can start thinking about what you can infer from the position on here. Okay, give me a thumbs up now if you've got your object on your CMD. Better. Okay, all right, we're gonna keep going. Keep working on it if you're in progress. What can we tell? So, first, any ideas? This is just the brainstorming session. We're gonna need a lot more information here, but what can we tell about, let's say, the lens? What population does it belong to? Main sequence or giant branch? Which one? Main sequence, yeah. Yeah, it looks like it's got to be on the main sequence. The giant branch turns off around here, and the lens is far, far, far from it. So most likely, odds are, our lens is actually a main sequence star. Do we think it's a massive star or a low mass star? Massive, yeah. It's pretty bright on the main sequence. It's not down here in the muck with all the other low mass stars. So most likely this is at least an intermediate mass main sequence star. Although we have to be careful, it could be that it's closer to us, and that's what's making it brighter, but it's falling nicely in the main sequence track, so that's a pretty good, reasonable assumption to make. But that's about as much as we can tell so far. I think we're going to need to look at some simulations to really dive into what understanding this color magnitude diagram in more detail. So Macy is going to come down to introduce the simulations to place into context what you've seen with a population where we know what everything is and what its physical parameters are.
Okay. So yeah, I won't talk too much about the galactic structure stuff since you all heard me talk about that earlier today already. But so we talked about how we use galactic models to generate a synthetic catalog of stars that all have their intrinsic and observable properties. And these are separated into the different populations of the galaxy. So in these catalogs, we're going to load up a new table here you have a cell to load the simulation table if you all want to get that running and let us know if you have any problems. In that table, we provide a lot more information than we have in the observed stars table because we have all of their intrinsic properties. So one of the first things that we want to do here, well, let's start by looking at some of the intrinsic properties of our stars. Sorry, getting back to the right part of the notebook over here. Okay, so once you have loaded up your simulation table, let's go ahead and make an HR diagram. This might be, if you're kind of new to color magnitude diagrams, this might kind of help us put it back in the perspective of the theoretical properties of stars that you might be more familiar with from classes. So let's plot an HR diagram. You'll put temperature on the x-axis and luminosity on the y-axis. If anyone could use help on this, go ahead and raise your hand and one of us can come around. If people want to give me a thumbs up whenever you've made your HR diagram, that would be great. We'll give it another minute or so. All right, so in our HR diagram, we are looking at the intrinsic properties of the stars. So you can see there's a lot less spread here than there is on the color magnitude diagram that also takes into account distances and extinction. So you can really kind of more clearly see the path of stellar evolution here between the main sequence, the red giant branch, and some white dwarfs over here as well. Yes, yeah, you might see a flipped version of this if you just plotted it as is default. On the HR diagram, we want to go from high to low temperatures on the x-axis. And this corresponds with the blue to red spectrum that we saw on our color magnitude diagrams as well. Are there any remaining questions or issues on this one?
Notice the log scale on that plot. Again, more mirrors to magnitudes.
All right, I think we're probably ready to move on. So We've already looked a little bit at some of the magnitudes in our star catalog, but I wanted to just again mention we have photometry in all of these filters from Roman. So there's a bunch of standard filters going from 0.5 micron to a little over 2 microns. This goes from some of the optical wavelengths to K-band in the near infrared. And then we also have the F146 filter. This is a very wide filter that covers a broad range of wavelengths between 1 and 2 microns. So when we're looking at our photometry and our different filters, these are the parts of the spectrum that each filter is capturing. You probably noticed in the catalog that there are a lot more 99s for missing magnitudes in those bluer filters. That's because these are highly extinguished fields in the galactic bulge, and a lot more blue light gets blocked by dust than red. So a lot of our stars become too dim to see at the blue end, but we can still see them at the redder end. So let's take our galactic model catalog and make a color magnitude diagram now, moving away from the HR diagram into something more analogous to our observational catalog. So this is very similar to the color magnitude diagram you already made, but we're going to make it from the simulation table this time. And then once you've created your kind of basic color magnitude diagram here, sorry, the page keeps moving on me. Once you've created your color magnitude diagram, we also want to separate out our galactic populations. So in our galactic model catalog, we have the population numbers that each of our stars belong to. So you can separate out into a simulation table of disk stars only. So these are stars with population numbers of 3 or greater. I'm sorry, I think someone's actively using this notebook, and since it's shared, it's, yeah. It keeps moving me because someone's running cells in it. And then likewise, we can separate out a subset of the simulation table for the galactic bulge, and this is population number 0. These population numbers are just the convention we use in SynthPop, so we can disentangle the bulge and disk stars. The numbers aren't particularly meaningful, it's just that they're distinct for different populations. So let us know, raise your hand if anyone has questions about making this simulation catalog color magnitude diagram. Yes. If you have your population separated color magnitude diagram, can I get a thumbs up to know where we're at? All right, we'll give it a little more time. Does anyone have any questions or issues as they're doing this? Yeah, we can look at both. We did have a plot on here that's looking at absolute first. Yes. Yep. Yeah, apparent magnitudes are all we can directly measure for real stars. So in the simulation table, we generate these from theoretical numbers, so we know the absolute magnitudes of our stars. But for observed stars, we don't necessarily know how those magnitudes are affected by distance and extinction. So we just have the apparent ones. All right, yeah, so if you made a color magnitude diagram in absolute magnitudes, you'll see that that looks a lot like the HR diagram, because absolute magnitudes are unaffected by distance and extinction, so they're much more reflective of the star's intrinsic properties. And then once we go and look at apparent magnitudes and separate out our populations, you can see there's a lot more scatter because of the distances and the dust, but you can also see some separation between the disk stars and the bulge stars here. So one of the kind of key features here is that we have a continuation of the main sequence for the disk stars in the blue. This is because we still have some high mass stars in the disk that have not evolved onto the red giant branch yet. And then for the bulge stars, these are all old, so any of those high mass stars have already moved over on to later stages of stellar evolution. So the next thing we want to do is plot on your target, both your lens, your source, and your blend magnitude onto this color magnitude diagram, and see if you can figure out from that which population any of your stars belong to. So you can just do this in the same cell you did this, or maybe copy the code down to the part of the template as your starting point, and then just add on the new bit of code to plot your star. Can I get a thumbs up when people are done adding your target to the CMD? All right, we'll give it a little longer. You probably already did this above on your observed CMD, so if you're using the same colors, you can probably just copy down those couple lines of code. So I'll go ahead and move us down to our solution for this. So in this one, we've actually plotted the observed color magnitude diagram and the simulation color magnitude diagram side by side. You can plot your points directly onto your simulation catalog if you want to. But I think you can see for our event in particular, this is providing some specific information about our lens star. So what are people seeing here? Any conclusions about the lens? Yep. Yep, our lens star here is very bright, and it's up on that part of the main sequence that none of our bulge stars reach into for this particular target. If you're looking at an event with a dimmer lens star, this might be harder, and you might be in that overlapping space where this color magnitude analysis is not necessarily going to separate the disk and bulge populations for every possible star. All right, are there any other questions or thoughts about this one before we move on? Okay, great. All right, so the next thing we want to do, we have a couple cells in here that will read in isochrones for you. So these isochrones show the expected apparent magnitudes for stars of a specific simple stellar population. So all of these populations have a single age value. That is the first number in the file extension here. This is in log years. The second number here in our file name is the extinction at K-band that we have applied to this population of stars. The next item is distance in parsecs. The next one is metallicity. Here we're just using solar for simplicity. And I've added a file extension here, ABmag, to make it clear that we have this in AB magnitudes for our photometry, which is the standard for Roman that we're using throughout this. So if you want to take these isochrones and plot them onto your color magnitude diagram, this can show a little more detail on why the parts of the CMD are populated by the stars that they are. So isochrone 1 here is a 10 gigayear-old population at an extinction of 0.4 NAKS and a distance of 8 kiloparsecs. So this is a very typical bulge population. These are stars near the distance of the galactic center. This is a typical level of extinction when we're looking towards the lower bulge fields for Roman. And then the second isochrone here is more typical of a disk population. So we've set it a bit younger, though there's a wide range of ages that the disk stars occupy. We're looking at an example of foreground disk stars here. So these are disk stars that are less distant than the galactic bulge. So we've put them at 4 kiloparsecs, just for this example. And since they're less far away, there is less of that dust in the foreground, so we've set a lower level of extinction here as well. So we'll take a minute or two here to get these isochrones plotted onto your color magnitude diagrams. Please raise your hand if you have any questions. Yes, on Zoom, do you want to try unmuting and talking? See if we can hear you. If that's not going to work, you can also send us a message on Slack. I think it'll work better if you send us a Slack message, please. Any Slack messages coming from me right now, I've given Jessica my computer, so that's not me. I went ahead and scrolled us down on our answers to our version of this plot, so you can check out what yours should look like. And, all right, yeah, does anyone want to shout out about what they're seeing here? Any thoughts?
Does it confirm our maps that we guessed earlier, or repeat it?
It is the left plot is plotted with both the isochrones, I guess. And the blue one is the first isochrone.
Yes. Yep.
Blue is the bulge.
Yep.
Stacey, it's a little hard to see from back here.
Mhm.
Can you zoom in on the left-hand side? I know, I don't know why.
I don't know if this notebook is live. All right, are we ready to move on? I think. Okay. Great. I'll go back to our notebook. So we have another aspect of this that we wanted to get to if we have time. It's a little complicated. What do you think, Jessica? Do you want to do the SCD part? Yeah. Okay. We'll see if we can come back to this one later. But this is another way to take a closer look at what we see from our isochrones. But let's go ahead and look at our kinematics. You want to take over?
Okay, so we've not quite exhausted. There was that other SED that we were talking about, but almost exhausted what we can do with photometry alone. Thankfully, we have two other dimensions of data we can look at in our catalogs. That's the astrometry in right ascension and declination. And basically, there's two sets, proper motion and parallax, that come out that we can kind of take a look at. So let's start with proper motion. Now, you've probably been shown plots of color magnitude diagrams and HR diagrams before if you've ever taken an astronomy class, but you've probably never been shown a plot of the proper motions for all the stars in the galaxy. That one we don't usually hit very often in our intro astro classes. So we're going to have to start with simulation efforts for sure here. So go ahead and, so the key things to remember are you have two proper motions in the simulations. Well, actually, you only have one proper motion in the simulations. It's for each star, it's proper motion in 2 dimensions. And that's not exactly what we'll see in the real catalog. We'll see blended proper motions if there's a source and a lens. So we'll keep that in mind. But let's start with just the simulated proper motions to get our brains familiar with it. So go ahead and plot proper motion in the longitudinal direction, proper motion in the latitude direction for all your simulated stars, and let's see where things lie. Again, ideally you would color code by bulge and disk, just like you did for the color magnitude diagrams. And if you're getting stuck on anything, here is the figure that I have. You can start to put your event on yours. And here's the code, maybe more importantly. When you go to plot your event on the table, just like we had blended photometry that got decomposed into baseline, lens, and source magnitudes, we have blended proper motions out of the events table for our microlensing events with proper motion from the total, the net flux, plus the lens and the source deblended. If you're curious about where that deblending comes from, it's derived from the equations right above. Once you've got your source and lens plotted on a proper motion, what we call vector point diagram, give me a thumbs up.
What is the additional points that you have plotted?
Yeah, so that's the one is the blended proper motion from the event, which is coming from the stars table. That gives the proper motion for the total lens plus source flux, how that moves on the sky. But remember, there's both a lens star and a source star, potentially with different trajectories. And we can't resolve the two. All we see is the combination of those two. But given the microlensing light curve, we can find the blend fraction that tells us what the source blend fraction is compared to the lens. That's this source flux fraction term, BSFF here. It's the flux of the source divided by the total. So for your purposes, you can just think of this as the flux of the source divided by the flux of the source and flux of the lens together on the bottom, right? And the two things have different proper motions, so we can use that BSFF, the source flux fraction, to decompose into the source proper motion and lens proper motion separately. And that's what's in the events table. And that's what gives rise to the blended proper motion in black, which you can barely see, and the lens proper motion in red, and the source proper motion in green. All right, who has their event on their proper motion diagram? Give me a thumbs up for those that do. Thank you, thank you, thank you. So we've also separated out the lens and, the bulge and the disc separately. So the bulge is in red and the disc is in blue. Why do they have such different proper motions? Does anyone know why the bulge has faster proper motions than the disc? How does the disc move? Rotates, right? So at a given distance, almost everything in the disc is moving the same way. So the proper motions are certainly compressed. Not many stars in the disc move out of the disc a lot. They're mostly moving in the disc in a big circle. So you see this compressed set of blue right here. Now, if you change your stretch or go to really, really low transparency on your points, low alpha value, you'll see it's kind of double noted. There's two bumps here on the disc. This is a peculiarity of this disc model. We were just talking with Matthew about this. The disc model we based this on has kind of a disc that falls off in the middle, right where the bulge picks up. So you get the near disc and the far disc. Near disc moving this way, far disc moving that way. And then why does the bulge have larger proper motions? If you take a star cluster or just about anything filled with points and you put them all at rest, do they stay at rest? No, they start intermingling. You just give them a little kick, a perturbation to kick it off, but then they'll start moving. And then over time, especially if you apply heat in the form of dynamics, perturbations from other things moving by, what happens to the velocities of the particles in the box? Which way? They spread out, yeah. They spread out, they move, they start having higher velocity until they thermalize, they equalize, right? Same thing happens with stars in the bulge. The bulge is old, it's been around for a long time, it's had lots of perturbations. Globular clusters flying through, nearby galaxies passing by, that's stirred it all up. And so the stars in the bulge, that's why the bulge is kind of round. It has had a lot more time to heat up, and therefore the velocities are higher. That's useful because we can use that properties to tell the difference between disk and bulge stars in some cases. For this particular event, the source is in a velocity space that's both consistent with the disk and the bulge. So we would have to combine the information from this diagram and our color magnitude diagram both to tell that the source star is definitely in the bulge. And the lens star, thankfully, our color magnitude diagram told us it was in the disk, perfectly in line with the disk kinematics here. So all of that is basically reinforcing what we think to be true, that our lens star is probably an intermediate mass star in the disk. Okay, one more thing to confirm is the parallax. Distance information is super helpful. Disk stars will be close by, usually. Sometimes we can see to the far side of the disk, but it's a little harder, especially as we look out of the plane. And bulge stars will be at the distance of the bulge, sort of 6 to 10 kiloparsecs. So where we have them, we've provided parallaxes in the table. So go ahead and try and plot the same thing. Make a plot of the lens and source parallax, and you can overplot that on all the simulated stars. This one's trickier. We only have one dimension for parallax, so it's not a scatter plot anymore. This one might be a histogram. Or you can choose to plot parallax as a function of magnitude. There's lots of choices here. This one did not render. No, that's disconnected. Okay, so there's a lot of different ways to make these plots. You can make 1D histograms, you can make 2D, combining parallax against the different proper motion vectors. That just happens to be one of my favorites. So this is parallax versus the longitudinal proper motion, and then over here is parallax on the vertical axis versus latitudinal proper motion. And again, I'm taking the simulated population and putting it in for disk and bulge as different colors and putting my object of interest on top, both the blended source and lens decomposed parallax and proper motion. So hopefully you're starting to get a handle between your proper motion and parallax plots on that. So give me a thumbs up if you've got some form of a parallax plot going. Not yet. Okay, good. And this one's definitely a brain teaser when you start trying to interpret this figure. Okay, if you're making good progress, you can also look at things like magnitude versus parallax, but if you're still working on your parallax versus proper motion, that's okay. We're just aiming at getting one of our parallax plots made with simulated parallax values versus what we measure. And I'll go back up to the proper motion and parallax and just flash some code. So this one was trickier to put your object on because you had to calculate the parallax for the lens and the source from the total. Here's the code that I used to do that. I converted my blend fractions and magnitudes to a flux for the lens and a flux for the source. And I used this equation right up here. The same holds for parallax and proper motion, the same equations for the blended. And then you can get out the blend parallax, the source parallax, and the lens parallax all separately. Okay, give me a thumbs up if you've got a parallax plot of any kind with your object on it. Okay, still working. see more? What was that? How many? Questions, points of confusion, I can clarify? Regina, any recurring questions on Slack? Okay. Okay, they're working hard. All right, if you're making good progress on your parallax plot, start coming up with theories for why you see these various structures on here between disk and bulge, and what you can say about your lens. Can you get its distance? And more importantly, can you get its age? Okay, give me one more round of who's thumbs up for those who have any kind of a parallax plot made with your objects on it. Okay, 2 more minutes. Okay, so hopefully you've got some parallax plots made of some kind. As I said, we plotted versus proper motion and magnitude. Let's start with the proper motion one. Parallax, this is distance, or inverse distance, versus proper motions in the 2 directions. Why, first of all, let's, what do we see about the bulge? What can we say about the distances between the bulge and the disk? Which ones are closer, which ones are further? This is the easy question. Which one? Bulge is further, yes. On average, why did it go back to the top again? Oh, that's fun. It deleted my plot. Oh, no. Oh, no. Okay, hold on. I got to go reload the tables again. That's all the way back up at the top. 1 second. That'll take a second. Okay, so bulge is further on average than the disc. What about that weird proper motion structure that we were seeing? Hopefully this will load now. Oh no, still not sim. Oh, because that's. Sorry, I'm gonna have to run through these again. Let's make those, and then this should load now. Thinking about it. Okay, so we saw that there was a lot more structure in the proper motion along the galactic plane. Again, that's galactic rotation. And you could see a very distinct pattern in the parallax versus proper motion. I promise, once it loads, you can see a very distinct pattern. Ugh. Always have a PDF backup. We do not. There we go. Okay, so let's look at the nearby stars first. Those are high parallax. The closest stars, right? Shortest distances. So these are all the nearby stars. Now we do see this trend. The stars that are close to us are moving with high proper motions, usually in the negative direction. That's moving to the west, if you care, if you're a amateur astronomer, you think about it that way. So there's also this second population of nearby stars that are kind of moving all over the place, but with kind of lower proper motions. Any thoughts about why we see this coherent, very tight stream versus this more spread out group? These are all disk stars. Why would there be two populations? What's the disk actually made up of? Different what? Thick versus thin disk. Yeah, the disk is actually made up of a couple of populations. Many different generations of star formation have been going on in the disk. There's ongoing star formation today. Those are super young stars. They're all very much confined to the disk plane. So they're all moving in this very nice, ordered, coherent rotation of the galactic disk. But there's a previous generation of stars and a previous generation before that, and on and on and on. The disk has been forming for the last maybe 8 gigayears, maybe not 12 gigayears, but 8 gigayears. So there's a thin disk, which is the young disk, and we think this is the thick disk, which is the old disk. Macy's triple checking in the simulations right now, or you can check too. So these are the stars that started in ordered rotation, but they've had enough time to kind of puff up. Perturbations have slowly led them to grow into what we call the thick disk. Okay, so for our object, the lens in particular, which is in red, can we say anything about its age? Give me a sense of scale. Anyone want to dare a guess as to whether it's young or old, or somewhere in the middle? You have 3 choices. Old? Why the old, for whoever shouted that out? I didn't see. Yeah, so the answer was old because it's in the thick disk. Yeah, so it's definitely not in the thin disk. So we can definitely say it's not young, or it's at least probably not young. Remember, these are all statistical statements. It's probably consistent with something that's intermediate age to old age, something that's part of the thick disk. Now, it's not, we say thin disk and thick disk, it's not really so distinct. It's kind of a continuum, a spectrum of star formation histories. One kind of bleeds into the other. You'll notice that's not the case for this simulation. This section's not really filled in. That might be a shortcoming of our model, or it might be reality. So this is the kind of plot we're looking forward to making with Roman that we can't make today so easily. What's the problem? Why can't we make this plot today with Gaia, which has parallaxes and proper motions? Anyone know? Yeah. It doesn't go deep enough. Yeah, so towards the bulge, Gaia proper motions and parallaxes are kind of restricted to up here, the top little bit of this plot. It's just the stars are extincted and too faint for the most part, and the bulge is very crowded. And Gaia doesn't do so well there. Good. Did I see another hand for the question? Okay, let's take a look at this parallax versus magnitude one, see if we can confirm our speculations. What gives rise to the structures here? What's this? Well, first of all, the bulge should be obvious. It's almost all at the same distance of 8 kiloparsecs with a little bit of spread. The disk is all over the place. But what gives rise to these weird streaks that you see here? Any thoughts? Remember, lines of constant distance move this way. If I have a whole bunch of stars at the same distance, what am I actually seeing? What's changing there when it's changing magnitude? What was that? Stellar type. What does stellar type come from? Temperatures, but also masses, right? For things that are on the main sequence at least, flux or brightness basically correlates with mass. It also correlates with temperature, fortunately, both of those things. So that's really neat. In this space, we can take something, the things that are at the same distance, and for the most part, especially with the disk, which is young enough not to have much of a giant branch, if you draw a horizontal line on here, you're drawing a line of decreasing mass to the right and increasing mass to the left. That's pretty cool. Now, what can you say about our lens, which is down here? From our color magnitude diagram, we already know it's probably not on the bulge. In the bulge, it's probably part of the disk. From the proper motions, that also agreed with that. So now what can we say about the mass of this object based on where it falls? High mass, low mass. Remember, our intuition before was definitely not low mass. Does that seem consistent? High mass, yeah, we're definitely more in the high mass regime. The really high mass stars are probably over here. Remember, over on this side. But these are kind of the intermediate to high mass stars that we talk about. Yeah, so if we had a lot of extra spare time or you want to work on this in a group project, you could use those isochrones you were looking at earlier to actually go find, you can put an isochrone on this figure and actually go find the mass that fits best with that isochrone and turn this position on this plot into a mass for your object. It's a secondary way of getting masses. It's basically purely from knowing the distance and knowing its luminosity. Okay, so let's get to the meat of it, which is star and planet masses and radii. Macy, do you want me to keep going on this one, or do you want to work through this section? Yeah? Okay, great. Okay, so you've all done in exercise 1 fitting of a microlensing event, and you extracted all kinds of parameters from that. In the binary lens fit, you were getting out Einstein radii, and you were also getting out relative proper motions and Einstein crossing times, TE. So if you have all of these properties, you can derive a lens mass. And we can, in principle, we don't even need to go through all this exercise of looking at the brightness. But if you remember, whose talk was it that was showing the 2 different ways of measuring lens masses, one from the microlensing event parameters, the other from photometry, and they cross, and hopefully they cross and don't not cross. If they don't cross, then you have a real problem, but hopefully they cross and you can draw a nice circle where they cross and get to your lens mass very precisely. That's basically what we're doing, is we're going to combine those 2 things together. Okay, so let me actually switch back to this one before I give it all away. Okay, so basically go ahead and calculate your theta E from the lens parameters you have in the microlensing event table, and go ahead and estimate your lens mass for the event that you're looking at. And then if you're enterprising, go ahead and calculate the planetary mass that you have if you assume a mass ratio of 10 to the minus 5, that your planet from the caustic crossing light curves gives you a Q of 10 to the minus 5. Okay, if you're still working on your lens mass and planet mass, here's the codes for the lens mass. Make sure you're checking your units along the way. So this one's theta E. Lens mass is about a solar mass. Does anyone have a planet mass yet? Give me a thumbs up. Thanks. This one here? That one? That's a subtraction. Yeah, remember mu rel is just the lens proper motion minus the source proper motion. It's the relative proper motion between the two. All right, who has a planet mass? Still working on it? Issues online?
No, I'm sending the equation. Okay, great.
Okay, so this is good. We had someone ask about why 365. Units matter. Proper motions are often given in milliarc seconds per year. Einstein crossing times are in days. Don't forget your units. Theta E should come out hopefully in milliarc seconds if you've done everything right, of about 0.6 milliarc seconds for this event. And then the lens mass needs to be converted with that fancy constant kappa we've seen, 144 milliarc seconds per solar mass. Solar mass per milliarc seconds? I can't remember now. Yeah, it is in the slide deck up above. Oh yeah, right there. Milliarc seconds per solar mass. So the lens mass should come out to about 1 solar mass, which gives you a planet mass, assuming 10 to the minus 5, a planet mass that's about 3 Earth masses in this case. Okay, so for a transiting planet, not a microlensing event, we can do something similar. It's not quite the same set of calculations, but from a transit depth, we can get a radius of the planet, and then we have to back out, if we can, we really are only being able to constrain the radius, not the mass of the planet. So microlensing and transits give you a little bit two different pictures of the planet that you are seeing. Okay, so let's come back to some conclusions. What were you able to figure out about your host star from the photometry and all the microlensing parameters? What aspects were ambiguous still? Even with all this data, there are still some things we can't answer. What can you learn about the planet itself? And we didn't deal too much with too much deblending here, but you could go through and deal with events that don't have as good of a blending parameter measurement or that don't have an Einstein radius. Those are all things you can think about for your group projects. So just to finish up here, I want you to take 5 minutes and talk with your neighbors about the answers to these questions, and then after that we're going to share out. So what are the things that you can learn about the host star, about the planet, and what things are still unknown that you would like to know about your system, okay? So chat amongst yourselves. 5 minutes, so 4:30 we'll share out. Okay, let's hear some responses. So these are some meatier questions. So let's go ahead and do hands raised rather than shout out this time. Let's volunteer. Who can I have the volunteer to answer the first question? What did you figure out about your host star? Anything? This is just summarizing what we've mostly already talked about. Who wants to volunteer? Go for it.
We estimated the mass and the age of like part of the galaxy we thought it was in. And then like once we figured out like okay, it's the disk, we figured out which disk population it was in.
Yeah, so we know it's part of the disk and not the bulge. We know roughly its age as a result. It's not a super old star from a number of different factors. And the last little bit was to get the mass out. We think we know the mass of the lens. And we have two different ways of determining that mass. One from the microlensing properties and one from where it positioned on the light curve. Did those two agree? Remember, our lensing properties said it was a 1 solar mass star. What did we say about the mass before that? Did we say it was high or low? High. And what did you all mean when you said high? In your head, what is high mass? Is 1 solar mass high? No, 1 solar mass is right in the middle, right? Yeah. So I think 1's kind of like above us is high and below us is we're all relative to us. We're egotistical that way, humans. So yes, we didn't quite get perfect agreement between the masses derived from the lensing event and the properties of the photometry and astrometry. Which one is right? How do we know? More data. Roman's not enough for you? $3.5 billion. Okay, yes, more data would be lovely. More importantly is, can we make the data consistent? We haven't talked about uncertainties at all, but in principle, you have uncertainties on your lens mass and uncertainties on all of your photometry. And we could turn these into those relationships that were bars that we were talking about before from the previous plots, previous talks. Each one is a bar. It's a thick bar because of those uncertainties, and hopefully we can sort of narrow down on the true mass of the object based on combining those two properties. Okay, good. What aspects are ambiguous for this particular event? Is there anything you really wanted to know about the host star that you don't have access to? Any hands? Let's see if we can get another one. We'll come back to you, though. Anything you wanted to know? Okay, we'll go. You had an idea. The metallicity. Yeah, I remember Jesse's talk had all the ingredients going into galactic structure. A lot of that galactic structure is correlated with metallicity. The bulge has low and high metallicities. The disk is mostly solar metallicities. We know nothing about this star's metallicity right now, and therefore, how do we put it into all of our understanding of planets? How would we go about getting information about the metallicity? Anyone know how we get metallicities for stars? Spectroscopy, SEDs. SEDs may be the thing that we didn't look at, that we didn't do, actually it's on this one, was exactly what you just recommended. Plot an SED. So let me see if I can get up to it. It did not render again. It did not. Let's see if I can make it. If you actually plot the SED of this star, no, it's not going to work. Can you send it around in the Slack, the SED plot? If you plot the SED of this star, it basically looks like this. This is brightness over here in magnitudes or flux, whatever you'd like. Sorry, you can't write sideways. And this is wavelength. The longer wavelengths over here, shorter wavelengths over here. What would a normal solar mass star look like in this space? Anyone know? I see hands, kind of bumpy things. Those hands and bumpy things are kind of black bodies, right? Something like that. Where the peak, where does this peak? What wavelength? Where your eyes see greenish, 500 nanometers, something like that. Now Roman doesn't sense over there, at least not with the wide field imager. We're over in this domain. So for a normal solar metallicity star, you would expect to see a long diagonal tail, bright at the blue end, faint at the red end, right? Now, what we actually see if you plot an SED from the Roman photometry is something that looks like this. This is a 1 solar mass star in Roman. Why would its SED look so different? Extinction, yeah. Extinction killed it. There's flux coming from the star out here, but it all got extincted away. It all got absorbed by the intervening dust. So the SED usually for unextincted stars could maybe be used to derive metallicities. Towards the galactic bulge, this is going to be much trickier. It's not impossible because Raman photometry is extremely precise, but it is highly degenerate with extinction. And you'll have to tease those two things apart. So spectroscopy is probably the name of the game. More data. Not with a $3 billion mission. You can go to our local 8 to 10 meter ground-based telescope and grab a spectrum in most cases. The only problem is the bulge is super crowded. What's the problem with telescopes on the ground? Atmosphere, yeah. The atmosphere blurs everything out, and it really makes it hard to see individual stars that Raman can see. Fortunately, we have a correction for that. It's called adaptive optics. So go find your local telescope equipped with adaptive optics and a spectrograph, and you can grab spectra of all of your interesting targets to get their metallicities. Good. Okay, let's go back down to our takeaways. Okay, so what can you learn about your planet? Anyone want to volunteer an answer? Mass and radius. Can you get both? Transits. Can you get both for transits? Transit just the radius, microlensing just the mass. So those mass radii plots, how do we get them on there? Tricky, huh? Yeah, it's tricky. More data is always the answer. So for the transits, you can follow up with radial velocities, spectroscopy, again, to get the masses for all those planets that you have radii for. What about the microlensing planets? Can we do the same? I see no, but why not?
Well, you can do a spectrum, but once the event is gone, and like they separate,
Yeah, so it's a source and lens during the event. Actually, it's more problematic during the event, because when you take a spectrum, you're getting the spectra of the background star and the foreground lens, and maybe there's a wobble from a planet in there, right? So that's challenging. Okay, so wait 10 years, and then they separate. Then you can see the lens. It's probably faint, but not always. So then can you do radial velocity spectroscopy of that to see to figure out the radius of the planet? It might be too faint, but let's say it's bright enough. The bottom line is you can't because radial velocities don't give us radii. They only give us masses. So for microlensing planets, that's a key shortcoming. We will never have radii. We will only ever have masses. But it's much easier to get the masses out for microlensing planets than to do radial velocity monitoring. Yeah? No, go for it.
If you have transits and radial velocity, and then you can try to draw a relationship between the radius and the mass using transits and radial velocity.
Yeah.
And you can try to translate this relation from radial velocity.
Right, so for those online, there was a suggestion that you can statistically derive a relationship from transiting planets between radius and mass of a planet, and then hopefully apply that to the microlensing events themselves. And that's absolutely true, although they do probe different types of planet populations, maybe not with Raman. Will we ever get an event that microlenses and transits in Raman? Anyone know what the probabilities are? Robbie? Is it 10 to the minus 1 or 10 to the minus 10? Probability that such a thing will occur in Raman. It's leaning to 10 and minus 10. Don't take any bets. Okay, good. Okay, so that's what we can learn about the planet. Let's see. So we gave you lots of, this was a good, easy event to work with. It had a theta E already measured, right? We could deblend everything. Not all events that you get out of Raman will be so easy. So one of the group projects that you might take on is looking at events that are a little less certain with fewer parameters. What can we derive in those cases? Or to actually propagate uncertainties through this process and figure out how we could assign probabilistically some assignment. What's the probability this star is in the disk or in the bulge, and what probability is its age, and what probability is its mass, etc. Let's see. Macy, you want to talk through the other group projects that we have available? I think I can try to bring them up. If you want to start just talking about them, I can just bring those lists up real fast.
Yeah. Do you want to talk about all 4 right?
Yeah.
Yeah.
Yeah, go for it.
Okay. So our first option for a group project is, I believe, titled GC event. This is going to be a lot like the notebook that we went through today, but looking at the Galactic Center. So in the Galactic Center, extinction is a lot stronger. There are a lot more stars, and there's some additional stellar populations to consider. So in here, when we separate out the disk and the bulge, you're also going to want to separate out the nuclear stellar disk as a distinct population to examine here. So that's the Galactic Center event. And then another one is a dark lens event. So you can pick a target that has blend fraction very close to 1 or exactly 1, and see what kind of information you can get if your lens is dark. And this will certainly be more limited than the event we looked at today. We had all kinds of information directly about our lens star, but you're going to have a lot less information in the dark lens case. So you can try to see, what information you can get out, and it'll be certainly less than we had here today. The next project is SED fitting. So this is part of that optional bit of the notebook that we didn't get to, but you're welcome to explore on your own. So in this case, you're probably going to want to do this using Python on your own local computer, and you should follow the installation instructions before you start working on this. You'll need a little bit of time to download some files and do some installation. So be sure to start that in advance if you want to do this. If that's going to be a large burden, just pick a different group project. And you can always take a look at these in the future when you have more time. So this is going to be an SED fitting project where you use isochrones from the SPICY stellar population modeling code. So you can use it to generate isochrones, and that will provide an SED in the Raman filters for whatever age, metallicity, extinction, and distance population you want to. And then the isochrone itself will have a bunch of rows that are all of those observable properties for stars of various initial masses. So you can compare the SED of your lens star, or whatever star you want to look at, to the SEDs of these model stars from the isochrones, and figure out the stellar properties like the mass and things like that. You can make this fitting process as simple or as complicated as you want. If you want to write a real fitter to do a bunch of exploration in the parameter space, you can, or you can just kind of generate a few isochrones and go through by eye and see what fits best, depending on how invested in this you are and how experienced you are in Python and with SEDs. And then the last project here is a binary event. So we do have a few binary events in our catalog, and we've provided light curves. So you can explore the light curves for your events. You could even run a fit on light curves if you wanted to tie this into the first hands-on session. And so for a binary event, you might have multiple luminous stars in the lens or the source system. So this is going to complicate your analysis, because if you're looking at the SED of 2 stars combined, that's not going to necessarily let you find an accurate single star from the SED fitting process that is a good fit to it. So you might find kind of some weird parameter space where your binary event sticks out on the color magnitude diagrams and other metrics. Yeah, anything else to add?
Okay, so that's it for today's hands-on session 2. So pick a group project if you haven't already. I think the clarification is you're picking one group project across project 1 and project 2. Just pick one of the group projects, and you can sign up on the Google spreadsheet that's been sent around numerous times. Don't put your name on 2 tabs, just 1 tab. Okay, and just another caveat on the one, you'll see all of them can be done in Google Colab except the one. If you're choosing the one that can't be done in Google Colab, there's 2 things you need: a laptop that's already set up to be able to do Python data analysis, and a good internet connection to download some files and software. Okay, so if you don't have those 2 things, don't choose that project. And then lastly, hopefully your experience today has shown you that when the Roman catalogs come out, the papers can't be written in 24 hours. It's going to take some analysis to do to figure out what your object actually is and to derive some physical parameters for it, but that's the fun part. So we hope you'll be able to use these tools as you go forward once you get the Roman data and start writing away. And let us know if you have questions. We'll be happy to take questions as you're working through your group projects on Slack for both hands-on sessions. And the notebooks and data are available to you indefinitely. So even post-Roman launch, all this stuff will still be here for you to play with. Thanks so much.